Welcome back, everyone! Today, we'll look at how to find the inverses of exponential and logarithmic functions and interpret them in real-world contexts. In the previous lesson, we learned that given the same base, exponential and logarithmic functions are inverse functions of each other, which is why their graphs are reflections of each other over the line y equals x. In Unit 1, you learned that two functions f and g are inverses if and only if f of g of x equals x and g of f of x equals x. These statements kind of remind me of these properties we saw earlier in this unit. B to the log base b of x equals x, and log base b of b to the x equals x. In fact, if we let f of x equal b to the x, and g of x equal log base b of x, these two pairs of statements are exactly the same. With these properties alone, we have proven b to the x and log base b of x are inverse functions. Let's practice applying these properties to check whether two functions are in fact inverses. Here are two functions, a and b. Let's verify using composition that these functions are inverses, which means that we need to prove that these two composition statements are true. Using a and b instead of f and g, these statements become a of b of x and b of a of x. With the help of these inverse properties, we must show both of these compositions are equal to x. Pause the video and try it out yourself. We find a of b of x by replacing every x in a of x with b of x, which results in log of 10 to the x minus 2 plus 5 minus 5 plus 2. We can cancel out those 5's and get log of 10 to the x minus 2 plus 2. Since the base of log is 10, we can apply the property log base b of b to the x equals x by releasing the exponent. Lastly, the 2's cancel out and we get x, which is exactly what we were hoping we'd get. To find b of a of x, we replace every x in b of x with a of x, which results in 10 to the log of x minus 5 plus 2 minus 2 plus 5. 2 minus 2 cancels and we get 10 to the log of x minus 5 plus 5. Time to use the other inverse property. Since b to the log base b of x equals x, 10 to the log of x minus 5 is just equal to x minus 5. Lastly, the 5's cancel out and once again we get x. Therefore, we have proven functions a and b are indeed inverses. Now let's practice finding the inverses of exponential and logarithmic functions. Example 2 is asking us to find the inverse of c of x equals 5 minus 6 times 3 to the x plus 2, and to state the domain and range of both c and its inverse. In Unit 1, we learned that to find inverse functions algebraically, we can follow these 4 steps. In this case, though, we're using c of x instead of f of x. Pause the video and try to find the inverse of c yourself. First, we replace c of x with y. Second, we swap x and y. Now we solve for y. Subtracting 5 on both sides and dividing by negative 6, we get x minus 5 over negative 6 equals 3 to the y plus 2. Dividing by a negative on the left side will simply change the sign of the whole fraction, so we can just write the minus sign on the side. To bring down the y and isolate it, we can rewrite this equation in logarithmic form, which gives us y plus 2 equals log base 3 of negative x minus 5 over 6. We finish solving for y by subtracting 2 on both sides. Lastly, we rewrite y as c inverse of x. Our final equation is therefore c inverse of x equals log base 3 of negative x minus 5 over 6 minus 2. Now let's find the domain and range of both c and its inverse. As we saw in our last lesson, a great way to visualize the domain and range of an exponential or a logarithmic function is by sketching its graph. Let's start by sketching the parent function of c, which is 3 to the x. We know its exponential growth because 3 is more than 1 and that it has a horizontal asymptote at the x-axis. Now let's identify the transformations. To make the transformations easier to visualize, we can rearrange this equation by writing the 5 at the end to show that the 5 is being added outside the parent function. Pause the video and identify the transformations yourself. Then, sketch the graph. First, we have a vertical stretch by a factor of 6 and a reflection over the x-axis, which turns the graph upside down and makes it approach the asymptote from below. Then we have a translation 2 units left and a translation 5 units up. This vertical translation shifts the entire graph along with its asymptote, which ends up at y equals 5. Therefore, we can see the domain of c is from negative infinity to infinity, and its range is from negative infinity to 5, non-inclusive. How do we find the domain and range of the inverse? Since we already found the equation of c inverse, we could go ahead and sketch its graph just like we did for c. But can you think of a simpler way of finding the domain and range of c inverse? We can just swap the original domain and range. We know the original domain automatically becomes the range of the inverse, and the original range becomes the domain of the inverse. We can make a quick visual confirmation by reflecting the graph of c over the line y equals x to get the graph of c inverse. We can see the graph ends up on the left side of the vertical asymptote at x equals 5, which confirms the domain is from negative infinity to 5, non-inclusive. And, as in all logarithmic functions, the range will be from negative infinity to infinity because the graph extends infinitely up and down. Now let's find the inverse of a logarithmic function. d of x equals 1/3 ln of x minus 2 minus 7. Pause the video and try this problem out yourself. We replace d of x with y, swap x and y, and then isolate y. The equation of our inverse becomes d inverse of x equals e to the 3x plus 21 plus 2. The parent function of d is ln of x, which gets vertically compressed by a factor of 1/3 and then translated 2 units right and 7 units down. We can then see the domain of d is from 2, non-inclusive, to infinity, and the range is from negative infinity to infinity. Automatically, the domain of d inverse becomes from negative infinity to infinity, and its range from 2 to infinity. To confirm graphically, we can sketch the graph of d inverse by reflecting the graph of d over the line y equals x, which shows that the inverse is an exponential growth function with a horizontal asymptote at y equals 2. To wrap up our lesson, let's look at a fourth and final example. Function beta represents the sound level in decibels produced by a sound intensity I in watts per square meter. Rewrite the equation such that it shows I as a function of beta. The equation given is beta equals 10 log of I over 10 to the negative 12. How should the equation look for it to show I as a function of beta? As it is now, this equation is showing beta as a function of I because the output is beta and the input is I. We know this because the output is always the variable we want to have isolated. Therefore, if we want to show I as a function of beta instead, that means we want beta to be the input and I to be the output. So the equation needs to be rewritten such that the new output, I, is isolated. Pause the video and solve for I. We start by dividing both sides by 10. Then, having in mind that the base of this logarithm is 10, we rewrite the equation in exponential form. Next, we can multiply both sides by 10 to the negative 12. Lastly, since we have two powers of 10 multiplying together, we can combine them by adding the exponents. Our equation ends up as I equals 10 to the beta over 10 minus 12. The process we just did feels familiar. It's kind of like we found the inverse. Guess what? We actually did! Our original equation showed beta as a function of I, and we found an equation that does the exact inverse. It shows I as a function of beta. Therefore, these are inverse functions. However, why didn't we follow the same steps as with the previous example? We didn't swap the variables as we usually do. Well, these letters aren't generic variables like x and y. The letter I specifically stands for intensity, and the Greek letter beta is related to the word decibel. If we had switched these letters, we'd call the variable inside the logarithm beta, but it would still need to mean intensity for the relationship to be true, which would be very confusing. Therefore, since both these letters carry meaning, we shouldn't swap them. Even though we didn't swap the letters, we did switch the input and the output. Function beta takes in sound intensity and outputs the corresponding sound levels in decibels, while its inverse, function I, takes in the sound level in decibels and outputs the corresponding sound intensity. In this lesson, we learned that the functions f of x equals b to the x and g of x equals log base b of x are inverses because they satisfy the composition properties of inverses, namely, f of g of x equals x and g of f of x equals x. And we used these properties to verify that two given functions are in fact inverses. Today, we also learned how to find the inverses of exponential and logarithmic functions algebraically, and how to interpret these inverses given a real-world scenario. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time! Hey.